Welcome to another session of animated lectures on arboviruses. This time we will focus on another mosquito-borne viral infection known as yellow fever. Please note that the reference materials at the end of this presentation were used to create the entire lecture slide deck and serve as sources for the information and images. Moreover, most of the images are AI generated.
Welcome to this animated lecture on yellow fever. Be sure to check out the sources listed at the end of the slides where this information was gathered. Yellow fever is an epidemic-prone, vaccine-preventable disease caused by a virus transmitted by infected Aedes species, Haemococcus species, and Sabethes species mosquitoes. These mosquitoes breed in domestic, forest, sylvatic, and semi-domestic environments. Due to its high impact and potential for international spread, yellow fever poses a significant threat to global health security. The viral illness is caused by an arbovirus of the family Flaviviridae, genus Flavivirus, encompassing positive single-stranded RNA viruses. The virus was isolated for the first time in 1927 in a male patient. Transmission is primarily by mosquitoes. After an incubation period of 3 to 6 days, YF infection can cause the onset of different clinical features, ranging from a self-limited or mild febrile illness with flu-like symptoms in most of the cases to severe hemorrhage and liver disease. Yellow fever remains a significant health threat, with ongoing outbreaks expanding into new regions in Africa and South America, affecting both rural and urban populations. According to the World Health Organization, 27 African countries and 13 Latin American countries are classified as high risk for yellow fever outbreaks. The potential for international spread to unaffected regions remains a global health security concern. A safe, affordable vaccine provides lifelong protection with a single dose. An estimated 67,000 to 173,000 severe infections and 31,000 to 82,000 deaths occur each year in Africa and the Americas, with most of the burden being in Africa. Main vectors are Aedes aegypti and Aedes albopictus, with forest species like Haemococcus and Sabethes involved in sylvatic cycles, especially in South America, where non-human primates serve as reservoirs. The yellow fever virus has 3 transmission cycles: jungle, sylvatic, intermediate, savanna, and urban. The jungle sylvatic cycle involves transmission of the virus between non-human primates, e.g. monkeys, and mosquito species found in the forest canopy. The virus is transmitted by mosquitoes from monkeys to humans when humans are visiting or working in the jungle. In Africa, an intermediate savanna cycle exists that involves transmission of the virus from mosquitoes to humans living or working in jungle border areas. In this cycle, a virus can be transmitted from monkey to human or from human to human via mosquitoes. The urban cycle involves transmission of a virus between humans and urban mosquitoes. Primarily Aedes aegypti, the virus is usually brought to the urban setting by a viremic human who was infected in the jungle or savanna. See more on the transmission cycle. Students should note this important aspect of yellow fever transmission. It will be emphasized in this lecture. Also, read the resources listed at the end of the animation. Recent outbreaks in Angola, DRC, Brazil, and Nigeria highlight the virus's capacity for large epidemics, with Brazil experiencing expansion near major cities due to ongoing epizootics. Human cases often result from spillover from animal reservoirs, with symptoms ranging from mild febrile illness to severe jaundice, hepatic failure, bleeding, and high fatality rates, up to 50%. Several different transmission cycles have been defined, depending on which host and vector species are involved in transmission. In the sylvatic cycle, tree-dwelling mosquitoes of Aedes spp. Africa or Hemagogus spp. Americas transmit the virus to non-human primates. In this cycle, spillover infection of humans occurs when they encroach on this jungle habitat. Conversely, in the urban transmission cycle, humans are the main hosts with transmission occurring via domestic mosquito species. The typical urban vector is Aedes aegypti, which also serves as the main vector for dengue virus transmission. If yellow fever is introduced into urban areas, large explosive outbreaks can occur, which can be difficult to control. In Africa, there is also an intermediate transmission cycle that occurs in rural areas, typically at the edges of forests, with humans as well as non-human primates affected, and transmission driven by domestic and semi-domestic mosquito species. Outbreak occurrence depends on the presence of a virus source, competent mosquito vectors, suitable eco-climatic conditions, temperature, humidity, rainfall, and susceptible hosts. Vertical transmission, transovarial, in mosquitoes can sustain the virus during inter-epidemic periods. Please read up transovarial transmission of yellow fever virus. Mosquito-host interactions vary by species. Aedes aegypti prefers humans, while Aedes albopictus feeds on multiple hosts, potentially bridging animal and human transmission. Compared to dengue, yellow fever produces lower viremia levels and shorter viremia duration in humans, which partly explains its limited spread despite shared vectors. Models predict high-risk areas based on vector presence, human demography, and mobility, aiding targeted vaccination and control efforts. The risk of yellow fever reaching major urban centers or spreading to Asia and the Pacific remains a concern, especially with increased travel and importation of cases. Gaps in surveillance and diagnostic capacity hinder early outbreak detection. Asymptomatic or mild cases often go unnoticed. Vector competence, ability to transmit the virus, and vectorial capacity, efficiency considering mosquito density, survival, biting rate, and environmental factors, are critical in predicting outbreak risk. Laboratory studies show that Aedes albopictus can be infected with YF virus, raising concerns about urban transmission if the virus is introduced into susceptible mosquito populations. Yellow fever viruses are genetically diverse with different genotypes in Africa and South America, affecting virulence and transmissibility. Compared to dengue, yellow fever produces lower viremia levels and shorter viremia duration in humans, which partly explains its limited spread despite shared vectors. Models predict high-risk areas based on vector presence, human demography, and mobility, aiding targeted vaccination and control efforts. The risk of yellow fever reaching major urban centers or spreading to Asia and the Pacific remains a concern, especially with increased travel and importation of cases. Gaps in surveillance and diagnostic capacity hinder early outbreak detection. Asymptomatic or mild cases often go unnoticed. The live attenuated YF vaccine 17D strain is highly effective, with 95% seroconversion within 30 days and provides long-term or lifelong immunity. Vaccination is the cornerstone of YF control, but global supply is limited, with recent outbreaks depleting stockpiles. WHO recommends vaccination for at-risk populations, travelers, and during outbreaks, with proof of vaccination often required for international travel. Vaccination coverage remains suboptimal. Estimates suggest 43 to 52% of populations in risk zones are vaccinated, insufficient to prevent outbreaks. Rare adverse events include viscerotropic and neurologic reactions, with higher risks in older adults. Contraindications include immunocompromised states. The duration of immunity was previously considered 10 years, but is now regarded as lifelong, though some debate persists about booster necessity, especially for certain groups. Limited vaccine production capacity and recent outbreaks have caused shortages, prompting strategies like fractional dosing and intradermal administration. Fractional dosing, example 1/5 of the standard dose, has shown to induce protective immunity, especially in outbreak settings, but is not officially recognized under international health regulations for international travel documentation. Intradermal vaccination is under research. It may offer similar immunogenicity with lower doses, potentially extending vaccine supplies. Efforts are underway to develop new vaccines, including plant-based subunit candidates, and to improve vector control methods. Vector control includes insecticide spraying, larviciding, biological agents, traps, and innovative methods like Wolbachia-infected mosquitoes, sterile insect techniques, and gene drives. Vaccinating non-human primates has been proposed as a supplementary measure, though feasibility remains uncertain. The WHO's Eliminate Yellow Fever Epidemics, i.e. strategy, 2017 to 2026, aims to expand vaccination, prevent international spread, and contain outbreaks rapidly through coordinated global efforts. Improving diagnostics, surveillance, vaccine access, and vector control are essential to prevent future epidemics. Climate change and urbanization may increase the risk of YF transmission in new areas, emphasizing the need for sustained vigilance and preparedness. A global initiative led by WHO, UNICEF, and Gavi to eliminate yellow fever epidemics by 2026. It responds to rising risks caused by changing epidemiology, mosquito resurgence, rapid urbanization, and increased international travel. The strategy is built around 3 strategic objectives. 1. Protect at-risk populations. Universal access to yellow fever vaccination. Use of risk assessments to guide preventive campaigns. Support for vaccine production and affordability. Prevent international spread. Strengthen international health regulations, IHR compliance. Protect high-risk workers. Improve readiness in urban centers and transport hubs. 3. Contain outbreaks rapidly. Early detection and confirmation. Strong surveillance and diagnostics. Maintain emergency vaccine stockpiles, 6 million doses. Rapid, coordinated response with partners. 5 competencies for success. To achieve its goals, IEI relies on affordable vaccines and stable supply, strong political commitment, high-level governance, and long-term partnerships, synergies with other health programs, research and development for better tools, alignment with global health agendas. The strategy supports 3 major global frameworks: International Health Regulations, IHR, for global health security, Global Health Security Agenda, GHSA, strengthening outbreak preparedness, Universal Health Coverage, UHC, ensuring resilient health systems.
Dear Dr. Abulu, promise, as I create this animated lecture, I can't do it without remembering the times you were with me, leading your group in qualitative research in Ekpoma and Uromi. Yes, you were my student until a few days ago, when you were suddenly translated to be with the Doctor of Doctors and the King of Kings. I therefore dedicate this work to your blessed memory. It is well.